Okay, 90 cent proportions. So this is taking us back a little bit. We've done confidence intervals and we did them for continuous random variables. We're going to do confidence intervals in a moment for discrete variables. Okay, so that's taking us back to chapter 7. So there is an element of chapter 7 in this unit where we're talking about confidence intervals for what we call a sample proportion. Okay, so we've got some facts about sample proportions there, and we'll refer to them as we answer them in the question. I think that's the best way to do it. So we have a sample of 10 people, and we found 3 of them had blue eyes. Okay, so P hat is the sample proportion. And so let's talk about that. Remember in continuous variables how we have X is the sample mean, and then mu is the population mean. Okay, so similarly in sample proportions, P hat is the sample proportion. So it's an approximation, it's an indication from the sample, and then P by itself is the population proportion. Okay, so it's similar language around that. Okay, state the observed value of P hat. Well, if we have 3 out of 10 with blue eyes, or we could express that as 0.3. So that's our answer to part A. Okay, part B. Find the mean and the standard deviation of P hat. So the mean, so given a population proportion P and sample size N, the sample proportion has mean P and standard deviation. Okay, so the mean of this is P, which is 0.3, and the standard deviation is the square root of P times 1 take P on N. Now let's take you back to chapter 7. Remember we have P, so the probability of success, and then Q, the probability of failure, which is just 1 take away P, or the inverse of P, we sometimes do that. So you could represent that as Q. So that's going to be the square root of 0.3 times 0.7 on 10. Punch out quickly. .3 times 0.7 divided by 10 square root of 0.1449, which is 0.145. Okay, so we've got mean, we've got standard deviation. Is P normally distributed? Is P normally distributed? So let's read, can we apply the central limit theorem here and perform a normal approximation? So if n is sufficiently large, then it's going to be approximately normal. Well, what makes it sufficiently large for a sample proportion? Let's have a read. For sufficiently large n, it's going to be approximately, that's the distribution. The closeness of the approximation depends on the sample size n, but also on the population proportion p. As a general rule, p hat is approximately normal if n times p hat is greater than or equal to 5. So this is the test. Okay? If the number of samples, 10, times the our observed value of p, 0.3, that's going to give us a value of 3. Okay? It is not larger than 5, therefore we have not performed a large enough sample to perform a normal approximation. Central limit theorem does not apply here. Is P hat normally distributed? No, as n is not sufficiently large. Okay, now the test is n times p being greater than 5, but our justification is never, because n times p is less than 5. Our justification is always with this language, whether it's sufficiently large or not. Okay? Any questions about what we've done today? So just a really quick summary. It's pretty similar to continuous random variables, where we're talking about mean and standard deviation, except now we're talking about the proportion. Okay, so it's the probability of a population affirming or denying something. So here we have, 3 out of 10 people that have blue eyes. That gives us a p of 0.3. The mean is always the value of p. The standard deviation takes this formula here, and we can do a normal approximation. We can do normal distribution calculations with this mean and this standard deviation, provided n times p is greater than 5. So you will be doing some normal calculations as long as it satisfies that contingency. Okay, let's get into it. 19.